Hi guys, this video provides an introduction to trees. I start out with a linked list because a linked list is actually a kind of tree. A linked list consists of nodes. Each node has a pointer to the following node. The last node of the linked list points to null, which marks the end of that list. There's also a head pointer, which points to the very first node of the linked list, also referred to as the head node. Now in terms of trees, a node in a tree typically has more than one follow-up node. The number of follow-up nodes for a particular node is referred to as the branching factor. Consider node 7, for example. Let's say node 7 has more than one follow-up node. So it points to node 3 and node 15. So node 7 has a branching factor of 2. It's easy to imagine that any of these other nodes could also have a higher branching factor and point to more than one node. Now a linked list is a tree with a branching factor of 1. That means each node has up to one follow-up node. A linked list is typically drawn from left to right versus a tree that is drawn from top to bottom. Here you can see an example of a tree. It's the opposite of a natural tree. A natural tree grows from the root at the bottom all the way up to the top, versus a tree in data structure has the root at the top and then grows towards the bottom. Now to point out, in terms of a tree, the root node is the head node, but it's referred to as root node or just root. In terms of a linked list, it's referred to as the head or head node. When we talk about trees, we often refer to nodes in terms of their relationships. For example, node 2 is the parent node of 76 and 39. That makes 76 and 39 child nodes or just children of the parent node 2. And remember that parent node and child nodes just focuses on the relationships between nodes. So 39 is a child node of 2, but it's also a parent node of 11. And because 76 and 39 share the same parent, 76 and 39 are considered siblings. Another example is the root node is the parent of its child nodes 2, 13, 45, and 7. And 2, 13, 45, and 7 are also siblings because they share the same parent. As you see, two nodes store the same value. So there's nothing in terms of trees that prevent a node from storing the same value. Just like in a linked list, we can have duplicates. In a tree, we can also have duplicates, depending on the particular tree properties and conditions. Now I mentioned the starting node at the top is referred to as the root node or just root. Any nodes in the tree that do not have any children are considered leaf nodes or just leaves. So these are marked in green here. Note when you look at the tree, don't just look at the bottom for the leaf nodes. Some leaf nodes are very high up in the tree, such as 13 and 7. So again, a tree in terms of data structure is drawn from top to bottom versus a natural tree that has a root at the bottom and the leaves at the top. A connection between two nodes is referred to as an edge. This is basically a pointer that points from node 2 to the node 76 here, for example. So this is an edge. When we have a sequence of connected edges, we refer to it as a path. So there's a path from node 7 all the way down to node 23. This is the path 7, 45, 83, and 23. In fact, there's exactly one path from the root node to every node in the tree. So we can see there's exactly one path from node 7 to node 76, or from 7 to 2, or from 7 to 11. If there were more than one path from the root node to a particular node in a tree, it would not be a tree anymore. Then, in terms of relationships, we also have ascendants. So for any given node k, its ascendants are the nodes on the path from the root node to that particular node k. So consider node 2, for example. Any nodes from the root node down to node 2 will be its ascendants. So node 2 has a single ascendant, which is node 7. Now if you consider node 4, its ascendants are all the nodes on the path from the root node down to node 4. So it will be 7, 45, and 83. Those are on the path from the root node to node 4. There are also descendants, which are all the nodes that follow a particular node k. Take, for example, node 2. Its descendants are all the nodes that follow this particular node. So 76, 39, and 11. If we consider the root node as node k, what are its descendants? Its descendants are basically all the nodes in the entire tree except the root node itself. So again, for a particular node k, its descendants are any node that follow this node on a path from the node to any of its leaves. Then there's the depth of a node. The depth is the length of the path from the root node to that particular node. So if you take, for example, node 83, this has a depth of 2. Because if we start at the root node, we have 2 steps, 1, 2. That is the length of this path. If you take a look, for example, node 11, the depth would be 3, because the path from the root node would be 1, 2, 3. And the root node is always at depth 0. Now there's also the height of a node, which is the length of the path to its most distant leaf. So consider node 2, for example. This has a height of 2 because its most distant leaf is 2 steps away. 1, 2. It has another leaf, but this is just 1 step away. Now if you take 83, this has a height of 1 because it has 3 children, they're all away 1 step. What is the height of the root node? The height is 1, 2, 3, or 1, 2, 3. So its most distant leaf is away 3 steps, and its most distant leaves are 11, 4, 23, and 18. So we can basically pick any of these. But important is when you consider the height of a node that you determine the most distant leaf. And the height of the root node is also the height of the tree itself. Then we have a tree size or node size. The size of a node is the number of its descendants plus the node itself. So node 2 has a size of 4 because it has 3 descendants, 76, 39, and 11, plus the node itself. The size of 83 is also 4 because it is 83, 4, 23, and 18. The size of 45 would be 5 because we have 45 plus 1, 2, 3, 4 descendant nodes. And the size of a tree is basically the size of the root node, which is the number of nodes in the entire tree. There are also levels in a tree. The level of a particular node is the length of the path from the root node to that particular node. So at level 0 is just the root node. There's always just a single node at level 0. At level 1, there are the child nodes of the root node. At level 2, there are the grandchildren nodes of the root node. So we basically consider the length of the path. If there's a length of 1, those are determine all the nodes at level 1. If there's a length of 1, 2, that determines all the nodes at level 2, and so on. This particular tree has a level up to level 3. So consider this tree. What is the root node? The root node is the starting node that is at the top, node 7. What are the leaf nodes? The leaf nodes are 76, 11, 13, 4, 23, 18, and 7. So leaf nodes are again nodes that do not have any children. What is the height of this tree? So the height of the tree is the length of the path from the root node to its most distant leaf. So in this case would be 1, 2, 3. So the height of this tree is 3. What is the height of 2? Now consider the most distant leaf. There are 2 pairs. To one leaf is 1, to another leaf is 2. So the height of 2 is 2. And what is the depth of 2? The depth is the length of the path from the root node to a particular node. So the length from the root node to node 2 is 1. So the depth of node 2 is 1. And what is the size of 2? The size of 2 is 4. It's the node itself plus the descendants. What is the level of 2? So the level of the root node is always 0. The level of 2 is basically 1. And what are the siblings of 2? So consider node 2, it has a parent 7, and 7 has 4 children, 2, 13, 45, and 7. So the siblings of 2 are the nodes 13, 45, and 7. What are the ancestors of 4? The ancestors of 4 are 38, 45, and 7. So a tree is a recursive data structure. A node can have up to n pointers to follow-up nodes of its own type, and those follow-up nodes are its children. How do we implement this? We could have an array of pointers that point to the children, but an array would limit the number of children, which would be okay if we say a tree has just a particular branching factor of, say, 5, then we know any node can have only up to 5 children anyway. But a lot of times in a tree, not every node has the full branching factor that is allowed for a tree. For example, the leaf nodes do not have any children. So using an array, we would just use unused memory, and it becomes very inefficient. The larger the tree gets, the more inefficient it is to use an array. Another way is to use pointers. The first pointer that points to the very first child of a node, and a second pointer that points to its first sibling. It's basically a linked list of siblings. Take a look at this tree. How would we implement this using 2 pointers? So we have a node, and each node has a pointer to its first child and to its sibling. So it would look something like this. The root node does not have any siblings, so the sibling pointer would point to null, and the first child pointer would point to 2. Then 2 would have also 2 pointers. Its first child is 76. Its sibling pointer points to 13. 13 has a child pointer that is null because it does not have any children, but its sibling pointer points to 45. Now 45 has a child, 83, so that is the child pointer, and its sibling pointer points to 7. Now to recap, a tree consists of nodes. The root node is a starting node, and we use family relationships to describe the relationships in a tree. There's also terminology. We covered edge, path, depth, height, size, and level. And the implementation of a tree is using pointers. For a generic tree like this, we have a child pointer and a sibling pointer. I hope you enjoyed this video. Thank you for watching.